Sheet molding compounds consist of 2 layers of resin paste with a flat layer of chopped and/or unidirectional glass fibers sandwiched between. Typical sheet molding compounds contain 30% glass fibers by weight. The resin pastes are typically either polyester or vinyl compounds. These compounds commonly incorporate fillers, additives, and other materials to reduce material shrinkage during molding, increase dimensional part stability, and to reduce overall material costs. Sheet molding compounds are manufactured in rolls of various thicknesses up to about 1/4 inch or 6 millimeters. Once manufactured, these rolls are used immediately or stored while the molding compound matures to the desired molding viscosity. Sheet molding compounds are produced sandwiched between thin polyethylene films to aid in handling. This film is removed from the sheet molding compound before compression molding. The direction or orientation of the fibers, the principal load-bearing elements, can vary ply to ply and between series of plies, and that orientation is critical to part performance. This is one of the many reasons why ply cutting was the first operation to be automated with the use of prepreg. Ply cutting operations have been closely integrated with automated nesting technologies. Once a composite design is finalized, it's loaded into nesting software. This software minimizes waste by nesting the shapes to be cut in the most economical pattern and governs the cutting operation. Cutting involves the use of either reciprocating knife, rotary knife, mechanical, ultrasonic, laser, or water jet cutters operating from a gantry. The gantry traverses a large table supporting the prepreg, sometimes multiple layers at a time. Cutting is rapid and accurate. Sheets and plies can be marked for identification during cutting, for later collation into bags called kits for layup. These kits are either used immediately for layup or placed in refrigerated storage for future use. A layer of catalyzed resin is often applied to the release-coated mold and allowed to cure to the gel or tacky state before the reinforcement is applied. This so-called gel coat is a protective surface layer through which reinforcement fibers do not penetrate. Special gel coat resins can improve flexibility, blister and stain resistance, toughness, and weatherability. As the gel coat cures, the reinforcement material, typically in the form of cloth or mat, is prepared for application by impregnation with liquid resin. This is referred to as pre-wetting. The pre-wetted reinforcement material is then carefully placed on the coated mold surface to minimize distortion during transfer. More reinforcement material and resin are applied as needed in this manner until required part thickness has been built up. Typically, the pre-wetted material is hand-rolled to achieve uniform distribution and to remove entrapped air. Because of the difficulty of handling wet reinforcement materials, the technique of placing dry reinforcement in the mold and then subsequently saturating it with liquid resin is also commonly used for layup. Once the T-fittings and vacuum medium are secured, a vacuum bag is mounted around the mold. The vacuum tubing is connected, and a vacuum is drawn on the bag. The vacuum pump source for infusion can range from small portable compressors to large stationary units. As the vacuum is being drawn on the bag, it is constantly worked to properly seal it against the reinforcement material. This ensures that minimal voids that can trap and reroute excess resin will occur. The bag is also inspected for leaks, and if any are found, they are fixed. As the vacuum pressure is reached, Small holes are cut in the vacuum bag over the T-fittings, and resin infeed tubing that has been clamped off is secured to these connectors. Once at the required vacuum infusion pressure, the infeed clamp is removed, and newly catalyzed resin is pulled into the vacuum-bagged reinforcement material, infusing it. As the resin infuses the reinforcement material, it is pulled towards the vacuum source, which is around the mold perimeter. A resin trap or traps are set up between the part being vacuum infused and the vacuum pump source. These traps capture any excess resin pulled from the mold as the reinforcement material is wet out, preventing the resin from reaching and ruining the vacuum pump. Besides being available separately and combined in fabrication, reinforcement fibers and matrix are also available together in what is called pre-preg, or pre-impregnated material. Pre-preg combines partially cured resin with fibers and must be kept refrigerated prior to use to inhibit further curing. Use of pre-preg simplifies and speeds composite layup and ensures higher quality parts. Fiber and matrix quantities are more accurately maintained, providing more consistent mechanical properties. Both continuous and short fiber forms of pre-preg are available. Layups may also be consolidated and cured using vacuum bag molding. In vacuum bag molding, a non-adhering plastic film, typically polyester, is sealed around the mold plate and layup material. An air valve or valves is then added to the plastic film for vacuum connections. Once ready, a vacuum is slowly created under the bag formed by the film. This vacuum forces the bag against the layup, drawing out entrapped air and eliminating voids. Additionally, it also draws out excess resin. Once full vacuum is applied, the mold is allowed to cure at room temperature or transferred to an oven or autoclave for curing. Vacuum is usually maintained during the entire heating and cooling cycle. Vacuum bag molding is effective in producing relatively large and complex shaped parts, including those having compound contours.